Nick Andreou here. Just as a quick introduction, I'm a professional engineer that happens to have the pleasure of being here at Production Modeling Corporation, where we're doing a lot of leading edge stuff, where we're an industrial engineering consulting firm with the idea of using technology to its fullest to get our clients efficient, lean, and have a good control of their systems. We use the term smart factories and smart cities, and really we need to understand what we're getting at when we're talking about smart. When you and I are trying to do something, we have the advantage of our eyes and our ears and our senses and our touch. So we know not to run into the wall because we see it. We hear things. We can feel the table is here, so we don't try to rush our hands right through it. When we're talking about a smart environment, we need to equip the environment, the system, the factory or the city or the complex with these kind of sensors so that we know that things are happening, where they're at, when things are going wrong, and also to have a way of correcting them. So everything has a limitation. If we had a utopia situation, we'd always get everything we want anytime we wanted it. Well, there are limitations, whether it's money or space or time. So in other words, we need to understand the bottlenecks that are in the way of us achieving everything we want. So on the right, you see simple things like conveyors that represent some of our new big business of warehousing and distribution, the Amazon type stuff, our classic manufacturing, cities, healthcare, other things. Each of those have a bottleneck in the system that we need to understand when it's happening and what I call the imminent danger that it might constrain what we're trying to get done. So if we start with how do we understand the system? First of all, most of these are physical systems. So we're not talking about an accounting system. We're not talking about preparing taxes. We're not talking about that. We're talking about physical systems in this case, whether they be a city, a manufacturing plant, physical systems. And we ask ourselves, do we have a good representation, a model of this space, okay, of the equipment? If we do, great. But really, is it accurate? Has it been updated? And so we strongly recommend doing a reality capture to make sure that we have things that are appropriately depicted in a model. Maybe it needs to be to 1 millimeter accuracy. Maybe it only needs to be plus or minus an inch. It depends on our topic. I also put in the word agents. And in this case, I refer to those things that are moving through the system. It could be cars on the road, people in a building, boxes or vehicles in a manufacturing facility. So you've got the building, the equipment, the processes, and the agents that are going through it. Physically, we need to have an idea of what they look like and what they're capable of. Once we have that, we really want to be able to model the system, okay? Represent all the factors that influence the results. Identify the constraints. And what I mean is that if we're looking at these boxes going through this distribution system, does it really matter what color the box is? Not for this discussion. Maybe it only matters that the flippers will flip this box this way and that box that way, and that the conveyor is moving at the right speed. So we want to model a system that reflects all of the things that are really influencing the results. Obviously, we want to be able to predict system performance. One person might be looking at this system and saying, how much energy does it take to run this operation? That's what he's modeling. That might be what's important to him. So they want to have gauges, sensors, information about that. Somebody else might want to know, well, how many boxes are coming out of the end of this thing? So what we're modeling is those factors that are our system performance. That's what it's about. Now, we talked about constraints. Everything has a constraint. Here you've got, 4 lanes of traffic going into one, and we understand that's how things work. That's how life works, whether it's time, money, physical space. There's a lot of really diverse reasons why we would consider system having a constraint. And if we happen to have a failure right at that bottleneck, if we happen to have a downtime, an accident, a machine break right at that bottleneck, we're dead. Okay, the bottlenecks cause a performance disaster if we have a failure there. If we have 4 lanes going down to 3 lanes, it's probably not the end of the world, because 3 lanes are still going to be much more capacity, feeding much more incoming traffic than what that constraint of 1 lane could handle anyways. So our point is that as we're monitoring these constraints, we need to understand the bottlenecks and make sure that the bottleneck areas are not at risk, because that's where disaster will happen. Okay, so if we're looking at these smart systems, trying to make sure we understand what a robust system is able to do, there are some things that we want to do. First of all, make sure we have a static CAD model so we understand the physical space of the building, the equipment, and so on. We want to make sure that we can simulate it and we understand those factors that we're really interested in, simulate those things, and make sure we understand what the constraints are within that system. So that if we need another lane, instead of going from 4 down to 1, going down from 4 down to 2 lanes, or if this one robot is the bottleneck, what do we do to make sure that that never goes down? To do that, we need to have sensors and what we call the Internet of Things. An array of sensors, just like your eyes or your ears or your touch tells you how to navigate systems. We need to equip smart systems with these kind of sensors so we know what's going on and things don't blow up in our face and you go, wow, how did that happen? Okay. In other words, an artificial intelligent system that understands behavior. We learn from an early age, if that pot handle is hot, you're going to burn yourself. Don't touch it again. An artificial intelligence system for a manufacturing might tell you that, hey, if this thing is vibrating and it's not supposed to be vibrating, chances are it's probably going to break, I don't know, in a day, in a minute, in a month. That's where the IE, that's where the artificial intelligence comes in, to have a system that understands when things are slowing down. Why? Things are heating up. Why? If there's a new frequency to this thing, why? In fact, it's kind of interesting that many of us can tell how an engine is running by its smell. Okay, for those of us that have had the experience of working on our own cars, oh, it's burning oil, or the belts are. So all of the different factors that come out of a system, we use AI in this case to predict what's going on. And of course, you have to respond. You can't just let it say, yeah, it's going to die, and let it die. So you want to be able to fix it. In fact, if we can fix the system, fix the bottlenecks, fix the predicted issues well ahead of time, tightening a bolt will make a huge difference as opposed to having to repair the entire axle. Okay. And that's the idea, that if we have the ability to understand what's going to happen and make sure we keep those bottleneck constraints from being a disaster, a small tweak now can save a disaster later. Now, there are very many diverse systems, and this is not just a manufacturing talk. Coming from Detroit, clearly robotics and automation, even electric vehicles, warehousing, some of the fun places that we're getting into now, such as vertical farming or architectural engineering, even the fast food industry, and one of our new areas of crowd management. All of the things that we talked about to this point, they all pertain to this same scenario of these very diverse clients. I'm going to take a minute to be a little corny here, and forgive me, this is just PowerPoint, so it only has a limited ability to make my point. Here is a digital image of a basketball. It's not a digital twin. It's not a model. It's just a picture. And if this thing was made out of wood or a painting on a page, it's still not a digital twin. Why? Because A basketball is intended to bounce. So if we wanted to have a model, a digital twin, a smart object that said, what does a basketball really do? Okay, we would need to know a little bit more about it. We would need to know, how does a ball bounce? Okay, maybe it's the hysteresis of the rubber. Maybe it's the air pressure inside the ball. Maybe it's the hardness of the floor. Anytime we are trying to create a digital twin, we need to program all of the performance characteristics that create this model. So if we want to know how the ball bounces, we need to know some of these things. Do we care that it has a Nike swish? Do we care that it has this color? Okay, not if our intent is to create a model of how the ball bounces. The same thing is true in all of the other examples of these diverse clients. Are we looking to understand how these plants are growing, or how parts are being delivered? Okay, we need to understand what are the factors that we need to model and model them. This is an old slide, but I really like it because it breaks out those aspects of a system that need to be modeled. For example, if we're looking at how do we load doors onto a car in the factory, do I really need an image of the engine? Maybe not. Or the seats? Maybe not. Okay, but I do need to know the center of gravity of the door, the mounting parts of the door. So my model of the product and the vehicle it's going into is specific to this example. Okay, and then the building it's going into, does it fit? The machines, the robots or articulating arms that are moving that door for loading it into a vehicle. And then the process, are we welding, gluing, riveting? What are we doing? So we need to understand the aspects in a digital format of those things that are involved in this process. So there's a number of different simulations. So if we look here, we'll see in this, where's my mouse? Oh, there it is. Here's a simulation, for example, of a large piece of equipment. It happens to be making cardboard components, cuts it, shapes it, stacks it, and so on. And this particular simulation was designed for a couple reasons. One, how does it look when I'm making these cardboard boxes? What happens when I want to change a 1 foot by 3 foot box to a 2 foot by 1 foot box, or a 3 foot by 4 foot box? What is the output? What does the machine look like? And this simulation does that. It also gives you some fairly decent visuals if you're talking to perhaps clients or investors. Okay, if you just wanted to know a number, you would not take the time to do all the graphics. So it depends on what we're trying to accomplish. So this is a piece of equipment. So let's look a little closer perhaps at a robotic solution. Okay, now here we've got a robot that we had designed that was taking these metal cabinets, and the job was to put those in place and then grab a grinder and deburr all the sharp edges. So this robot is able to pick up that cabinet, put it down, pick up a grinder, and then go around the perimeter of this cabinet. Now, why am I showing you this? Because here we have a robotic solution, but for a lean engineering idea, says, is this the best way to do it? Okay, just because it could be done this way, just because the client said this is what they want to have us develop, we did. But from an engineering standpoint, we said, yeah, let's try something else. How about instead, since we already proved that the robot can pick up the cabinet, how about if we pick up the cabinet and then have a stationary grinder and then run the cabinet all around the grinder, and we just reduce the operating time of this cycle by 50%. Greatly reduced it by doing some sweet engineering and being able to understand what the factors, what the bottleneck of the system was. So when we understood what the bottleneck was, we said, well, why have that artificial constraint in there? We're able to greatly reduce the time it took. All right. So in addition to the equipment, of course, there is the ergonomic piece. Now, this is a longer presentation. I'm not going to go through each slide. The intent is to say that when we are looking at a system, people play a huge role. How are these people involved in the human interface to the equipment? Okay, some of these are standard slides. I'm sure some of you have recognized these from before. But understanding the 5% female to the 99% male, their reach zones, their abilities to do work, um, we put those into a work environment, and we'll try to understand what are the constraints. Here's a job that they're doing. We put 4 people to assemble these parts. So we're combining the people with the environment, with the equipment, with the parts, with the tools, and we're looking at, can they do the job, the people, can they do the job without getting hurt? And what is the throughput of the system? That's with 4 people. Well, what if we did this now with 3 people? Okay, now let's run it. Are these people going to get the job done within the prescribed cycle time? Will they get hurt? Will they be asked to do more than is reasonable? Can this job still get done? So the point is that maybe we don't need 3 people. Maybe we don't need 4 people. Okay, our job is to figure that out. And when we look at these different ideas, we are starting to rate, are the people getting hurt? Are they falling within their posture limits? And so I'm going to run to the end here. You see different evaluations, and not our intent to read all these words, but you see that different tasks will yield a positive situation for this person. But you see this person leaning way over, that can't be good. So at the end of the day, we have an assessment of the different tasks that people are doing. And we're saying, okay, in this case, this is green. This person's workload was acceptable. This person's workload was not acceptable performing this task. Constraints come in many forms. It's not just money or space, but it's also what can the person do safely. Finally, when we get to the warehouse example, we're back to understanding there are a lot of different ways to look at a system, and us modeling it is up to us to figure out how to do that. One of the things that we're experiencing these days is crowd simulation. That's one way of talking about how people move. There is crowd safety, there is mobilization, maybe in a large complex or a school or a mall. How do we understand what is going on in there? Okay. If we were to take a building like a school or a mall, there's not moving parts, not really. Okay. It's the people that are moving. So here we have a series of constraints that may be the doors, the elevators. Okay. So there are different ways to look at these. People moving, these are not ants, those are supposed to be people. Density of the population, the time it takes maybe to evacuate or to go from place to place. So here's an example of a new infrastructure, new sports complex. And we're looking at, how do these 80,000 people come and go from this facility? Should these arms, should they be wider to handle more people? Should these corners not be corners, but should be radiused so that they can get around it faster? So this is part of our ability to simulate a system and come up with a smart design. Okay, let's take the next step, evacuation planning. So here we have a model of how people are expected to exit in the case of an emergency. In this case, the building is not critical. It's just a block. What is critical is the traffic, the people, where are they going? You see, they're all heading in the same direction. They're leaving some place. So our ability to simulate that is huge. This bottom one is and you can see here in this one, people are crowding up and they're getting blocked, which is part of the issue when you're trying to have emergency planning. This is a 3D image down in the bottom left, and you're going to see in a minute people flying up into the air. Well, they're not really flying. We're simulating what the elevator performance would be like as they go through this rather tall building. And they come as groups, lunchtime, coming into work, leaving from work. So the time frame for how we handle people movement is, there they are. You see them flying in the air up down here? Okay, it's kind of funny. So that's the point of this simulation. There's a couple of things that we really want to look at. in the Internet of Things, we want to be able to sense what's going on, particularly in the bottleneck operations. We need to understand the cycle time. Okay, when we have a machine being controlled by a program, by PLCs, programmable logic controllers, and it says that this machine should move in 2 seconds, and we're measuring it, and it moves in 4 seconds. You go, hold it. This is supposed to move in 2 seconds. Why is it moving in 4 seconds? Is the pressure too low? Is there a leak in the hose? Is there dirt in the gears? Why is this not performing the way it was designed? From a cycle time, that sounds pretty straightforward. And the noise, we talked about whether or not you're hearing something that shouldn't be happening. Some rattling, something is heating up that shouldn't be heating up, or some smell, as we talked about, maybe rubber being burned or something off kilter. So the idea is, if we can sense those features that can predict failures, particularly in our bottleneck operations, we should be able to identify what's about to happen, and especially if we have history with this equipment. And we say, we have sensed that when it heats up to outside of the normal range, it's got another week before it fries. Or maybe it's 2 days, or maybe it's 2 months. The point is, the AI piece of this will give us insight so that we are not surprised by the failures. There's another aspect too, and that is that, well, if the maintenance schedule says change these bearings every 6 months, well, what if I don't have to change them every 6 months? What if they're doing just fine? Maybe I'm not using that machine as often as I need to. Why do I need to tear this thing down and replace the bearings when it really hasn't worn out? So now there's a simulation that we've done that shows this is how the operation runs. We have a distribution of data that says this is how people arrive to work. This is how our tolerances will perform when we create parts. Okay, but is that really reality? So we do a simulation. We pay the money to have experts produce the simulation of a system, but then, well, did everybody come into work today? Maybe Sally did not come to work, and so now you've got to juggle things around. I did have the opportunity to be a production supervisor in a production plant, and the idea that somebody didn't come to work, that happens every day, and you have to understand, who's got the skills to do this job or that job? How do I accommodate this variable? And it's okay if you've got 20 years experience on the job, you know exactly how to respond. But there's fewer and fewer people with this 20 and 30 years experience, and we do have simulation models that tell us exactly how this digital twin of reality works. So the point here is, let's feed that in on a daily basis. It's okay. We know who really came to work today, and we know what we're really building today. Maybe we're building coupes, not sedans, or maybe we're building convertibles. What we're really building today, with who really came into work, and what equipment is working. Did this break? Is this functioning? Is this one down? Okay, that's not what the model said when we paid for it a year ago. And then, of course, we don't necessarily have to work 8 hours. Maybe we work just this one department an extra 2 hours or 3 hours overtime to make up for it. My point is that by using the Internet of Things and sensors, we can predict how to keep our equipment running. And secondly, we can take inputs from our daily, everyday situation and feed it into the beautiful simulation models we have and get an update on, reality says this is our workforce today. This is the model mix today. This is the equipment that's really running, and we have the flexibility of running some hours. Okay, let's use the technology, let's use the simulation, the digital twin, to help us optimize our operations on a daily basis. And that's part of what we can achieve. The components of a smart factory or a smart city, and to me, a smart complex is very ripe for the taking, is where we can apply some of these simulations, understand what the bottlenecks are of the systems and improve our clients' proficiency and their efficiency considerably with these techniques. None of these are, I'll call it rocket science at this point. We do these and we just need to apply them. We're not really inventing anything that doesn't exist, but we do need to implement them. And if we can avoid the danger of crashing at bottlenecks, avoid the danger of not understanding our digital twin and therefore not optimizing it, we're flushing money down the toilet. And that's it for my scheduled speaking part. Brian, are there any questions?
Yep, thank you, Nick. And we did have a few questions come in throughout the presentation. We'll get started with those, but please, if you have any questions that you want to ask Nick, like I said, use the chat box feature in the top right with the bubble and submit your questions. But first, Nick, the first question that we had come in, do the terms smart factory, smart city, and digital twin all mean the same thing?
It can be, of course. The idea of smart, basically, my introductory words were that we're trying to get automated systems to behave like a person would, sense what's going on around you and respond. We think that Android type robots, we give them eyes, we give them ears, we give them cameras, so that they can be smart, not just sensing, but then doing something with that information. So the artificial intelligence piece is part of what makes it smart by saying, yeah, I see, I hear, I can feel what's going on in this system, and now I know what to do about it. So the digital twin, yes. The smart factories, yes, they really are part and parcel of the same thing.
All right, thank you, Nick. The next question we had, does this methodology apply to all industries or market sectors? This person says, I am in the medical services field, and we are always challenged to reduce cost, reduce patient wait times, but also retain the great patient care. So I guess this means, like, what do you recommend?
Mm-hmm. And I think that's a great question because I've had the pleasure of, even though we grew up, say, here in Detroit, and we see heavy automation in the auto industry, our exposure has gone to many other industries and market sectors. And we recognize that the principles of lean engineering, sensing what's going on and having a model works very well. And I cannot think of a limitation. In the healthcare industry, for example, making sure that we have the people that are there to serve you when you need it is imperative. And I know that we don't have an unlimited supply of doctors and nurses, but perhaps many of us have had the experience of going to Disney World when there were huge lines. And then industrial engineers came in and did this callback. I forget what they call it, but the point is they were able to organize, if you come back 20 minutes from now, you can come into the line and come in at the head of the line. The industrial engineering scheduling has flattened out those long curves and has made it a lot easier for everybody. If you go to a Jimmy John's, you see they hire like 10 people for like an hour and a half during the lunch rush and then send them home. And everybody's happy to do it because they understand what the demands are of that peak. So back to the healthcare industry. I think that by modeling the situation, the flow of people, the delivery of service, there is much that can be modeled and improved by being able to respond to that intake. So yes.
All right, thank you, Nick. Another question we had, it says that the simulation showed in the presentation represent a snapshot in time. How can they really help my operations with day-to-day fluctuations and unpredictable variables?
It kind of goes to that last piece where we're putting sensors in the operations and feeding those to a model. Now, there are different schools of thought. Some suggest that having a separate computer that is running a simulation of your system and you input it at the beginning of the shift and you say, yes, I've got 14 employees showing up today, not 17. Now what can I do? So inputting it one time in the morning and then running your operation. There's another school of thought that suggests that you tie it in to your ERP system, your EMS system, so that when people actually badge in, that information goes into your simulation and will actually, feed your operations. Uh, I love that. I don't know that we're ready for that quite yet, but I believe that a step along this journey is for us to be able to, at least on a daily basis, update our live simulation models with today's current scenario. And eventually, we'll get it to feed with real data, with inputs that are automatic. And we don't need to even do that part manually.
Okay, thank you, Nick. Another question is, will the slides be shared? If not, can you show the first four points again? So I'm assuming it's the 1, 2, 3, 4, yeah.
Capturing the model.
Yep. But to answer your question real
Making
quick,
sure that
there's going to be a recording of this presentation that will be shared with you if you want to review the slides. But thank you. Go ahead, Nick.
Yeah, and we can certainly provide the slides probably in a PDF, which means that the videos won't be of any use to you because they won't go along with the ride. But certainly I think there's about 17 slides to this that can certainly be available.